Today, we're going to talk about one application of definite integrals, and that's to average value. And so what we want to think about here is think about some kind of function. And we have this like little function, it's wavy. And we have this function on the interval from A to B. And let's pretend like it's always positive. So what I like to think about this is I like to think about this as a graph of a mountain range or a graph of an ocean. And I want to ask myself, well, what would happen if that mountain range was kind of like sand? It was like a mountain range made out of sand, and we just kind of shook it until it all flattened out. So instead of having peaks and valleys, it was just like flat land, but took up the same amount of space. It was made out of the same amount of sand. Where would it level off? How tall would it be when it leveled off? That's what the average value of a function is. It's if I made that function out of sand, I kind of shook it until it averaged out. That would be its average y value, and that's the average value. I also like to think about this in terms of waves. So imagine you had a little fish tank and you had shaken it around so that this was the like wave pattern that you had. The average value is going to be how high is that water when that tank settles down. So what would that like settled height be? So average value is essentially telling us what would the height of our function be if it was something kind of liquid and was able to flatten out at a value, what value would it flatten out at? So when we think of finding averages of things, here we're thinking about finding an average y value, but we have infinitely many points on our graph. So we can't treat this just like we would have treated things before, where if I wanted to find my average grade, I would add the like 5 grades together and divide by the number of grades, because we have infinitely many things. But we can kind of start with that same idea. So if I didn't have infinitely many things, if I just had a finite number of points, the way that I would find the average is I would add up all of those points and divide by the number of points. And so to add up the points, I'm going to call this a sum. And I'm going to think about adding these as y values on a function. So this is a function, and the x sub I are just like the points that I'm taking on that function. Okay, so how can we deal with this? So we might want to say, well, we have infinitely many points on this function, so let's take a limit. Okay, this looks vaguely similar to an indefinite integral, but we remember to a definite integral, sorry. We remember a definite integral looks like a sum of delta x times f of x sub I. So these two ideas are similar-ish, but they're not exactly the same. So what I'm going to do is I'm going to try and tweak this first thing. This first thing is my average value. This would be my average of all my y values. So this is the thing that I'm trying to figure out today. So what I'm going to notice is that the delta x is kind of the thing that's missing in my top equation. We remember that delta x is b minus a over n. Okay, I have an n in here. So let's solve for n. So I can multiply both sides by n and then divide by delta x. So n is b minus a over delta x. So I can replace n by that. I'm just going to be super lazy. I'm going to erase it here. So we're going to have b minus a over delta x. Now I can like flip this and move the delta x up top. So if I do that, I'm going to have a limit as n approaches infinity of a sum f of x sub I, that delta x moved up top, over b minus a. Oh, this is interesting. So this top part looks just like this, but this was the definite integral from a to b of f of x dx. So what it looks like is it looks like our average value is just an integral from a to b, f of x dx. That's all that blue stuff over b minus a, over the width of the interval. That's kind of cool. And that's exactly what this definition down here tells us. The average value is that integral from a to b over b minus a. So the integral, think of that as adding up all the values. Just like if you were trying to find the average of your grades, you would add up all your grades, all your test grades, and you would divide by the number of grades you had. And so the adding up is like what our numerator is doing. The dividing by the number of grades is like what the denominator is doing, because that's telling us the width of our interval. Okay, so all of that derivation that I did, you don't have to memorize. It's useful to see, but you don't have to remember that. Okay, So let's just start computing average values of functions. So for this first one, we have sine of x on 0 to 2 pi. We can also write this equation as, I can just pull that denominator out. It's a little bit nicer to write it as b minus a times the integral. This is how I oftentimes do it. So in this case, my a is 0, my b is 2 pi. So I'm going to have 1 over 2 pi minus 0 times the integral from 0 to 2 pi of sine of x dx. Okay, well, now I just have to compute that integral, keeping a 1 over 2 pi out front. That integral, the antiderivative of sine is negative cosine. I'm going to plug in 0 and 2 pi. So I'm going to have 1 over 2 pi times negative cosine of 2 pi minus negative cosine. So that'll be plus cosine of 0. Cosine of 2 pi is 1, so we're going to get negative 1. Cosine of 0 is also 1. So the negative 1 plus 1 is going to give me 0. I'll have 0 over 2 pi, which is just 0. The average value here is 0. That's weird. Let's look at the graph. So the graph of sine of x looks like this from 0 to 2 pi. So the average value, that's not 0. Sorry, that's pi. The average value is saying, okay, if this were my like little ocean tank and I like shook it all out, where would things flatten out? Well, notice this is a little bit hard to think about as an ocean because we've got kind of a valley there. But if this all shook out, it would shake out at 0 because the stuff above sea level and the stuff below sea level would like balance each other out. So this is what the average value is saying, that the average y value of this function is 0. And the way you can think about this in this case is that each y value, each positive y value has a corresponding negative y value, and those are canceling each other out to give an average of 0. Okay, that kind of makes sense. If we look at this next one, so we're going to have 1 over 8 minus 1. 1 is my a, 8 is my b, integral from 1 to 8. The cube root of x is x to the 1/3 dx. So we're going to have a 1/7 out front from this guy. Antiderivative of x to the 1/3 is x to the 4/3 times 3/4. This one does not look like it's going to be pretty. From 1 to 8. So we're going to do 1/7 times 3/4. 8 to the 4/3 minus 3/4. 1 to the 4/3 will just be 1, so we'll just have a minus 3/4 there. When I compute that value in a calculator, I am going to get 1.607. Not so pretty, but that's okay. We'll look at this one and the next one on the graph in just a second. So this last one, I'm going to do an integral. Well, I'm going to have 1 over pi over 4 minus 0, integral from 0 to pi over 4, cosine of 2x dx. I'm going to have to use u substitution here. U in this case will be 2x. du over dx is 2, which tells me du over 2 is dx. So I'm going to get 1 over pi over 4, which, yeah, I can keep it like that. Times I can have the integral from x is 0 to x is pi over 4 of cosine of u du over 2. I can pull that 2 out, that 1/2 out front. So I'm going to have 1 over pi over 4 times 2 coming from this guy. The antiderivative of cosine is sine of u. I'll replace the u with the 2x. These are x values, so from 0 to pi over 4. So we have 1 over, this is the same thing as pi over 2. Sine of 2 times pi over 4 minus sine of 0. Sine of 0 is 0. This will be sine of pi over 2, so this will be 1. So it looks like I'm going to get 1 over pi over 2, which is 2 over pi, or in a calculator, 0.6366. Okay, let me pull up a calculator or a graph here, and just let's look at those last two examples on a graph. Give me just a second. So if we look at example number 2, that cube root of x, this is the graph that we get. We have limited ourselves to the interval from 0 to, or from 1 to 8. So let's look at that. Okay, so this is our little graph. We're looking at the average of these y values. The answer we got out was 1.6 to something. So let's see, maybe 1.6 is somewhere in here. So that's what our average y value is. If we added up all these values and divided by the length of the interval, it's kind of a little bit hard to see sometimes. Let's maybe look at that cosine example as well. So we have cosine of 2x for 0 to pi over 4, pi over 4. So we notice we get this tiny little graph here. Our average value should definitely be something less than 1. In this case, we got 0.63. So we're saying that the average y value is like 2/3, close to 2/3, somewhere up here. It kind of seems like our average y value here if we added kind of all this area up and divided by the length of that interval. Okay, so we'll get some more practice with this in class, and we'll see something called the mean value theorem for integrals in class as well.